So the project team is our company, Energen Tech, a company called Robotic Technologies of Tennessee, Gay Engineering, Jim Dido, who's here to answer all the hard questions, Miller Electric and Hobart, and then a company called Zanner. And if you want to see a really interesting website, go to their website. It's the letter A, Zanner.com, and they build these weird shaped buildings all over the world, and it's amazing the stuff that they actually do. Okay, so I'll give you a little bit of background information, talk a little bit about the system design, both from the standpoint of the robot system itself and the control system, talk about the virtual environment we're using, and then show you some of the results that we've had. Now this is really a small feasibility study. It isn't a full-blown RA project, so they call it a panel project for those of you familiar with NSRP. So looking at the background, this is kind of interesting to me because what we're now starting to call cobots, or robots that are collaborative with human beings as opposed to independent or semi-collaborative or just flexible automation type robots, are just now coming into being so strongly in the whole business world that NASDAQ now has a special fund for them. And the first day that fund was in operation, they had a cobot, this guy right here. Universal Robots makes that, and that's, by the way, the arm that we have on our system is that same arm. Ring the closing bell at NASDAQ on that day. And part of the reason for that is kind of seen here. This is a I call it a semi-collaborative robot, sort of made by a mainstream company. Motoman produces this one. And this is a small, low-cost collaborative robot. And the difference between these two you can see kind of immediately in terms of cost. Where the growth is in this market right now is in the small, relatively low-cost versions of these robots, and partly because the old line robotic companies like Motoman, for example, have been around for a while. They're very conservative and they're very risk averse, so they don't really want to hand over control of the robot entirely to a human being with a computer in the way in case it were to get loose and hurt somebody. So the place where the big growth is right now is in the small startup companies and low-cost portable robot systems, and the market for the large scale cobot systems has actually shrunk in the last year by 20%, where the market for the small sort of agile cobots has grown by a factor of 5 in the last year. So there's a huge market growing, and I think we're seeing a lot of innovation in this arena. I'd like to show this slide when I talk both about flexible automation and about portable robots. Robots have been around since the 1970s. That's when the auto industry really got going on automating. But they still basically look the same as they did back in those days. That's an IRB 1410, I guess, from 2013 picture. And they all require extensive programming, and so they are only economically viable when you're going to make tons and tons of parts. So as an example, Chrysler did a body changeover for their Neon vehicle, and they spent about $2.4 billion on that. Half of that $2.4 billion was robot programming costs. So if you're going to make a few of a kind parts, you can't amortize that huge cost over a large number of parts, and that's why in heavy fabrication, shipbuilding, for example, and so forth, robots have traditionally just not been very effective because of this massive cost. So we've been looking at different ways of trying to kind of fix that problem. So standard robot programming is time-consuming and expensive, cost justified by high production runs. One of or few of a kind are not feasible. But the payoff is in this little example up here. If you look back to the 1960s, the average sort of sedan sold by the auto industry in the US before robotics cost about $3,000 and had about a 12,000 mile warranty on it. Today, oops, I did it again, Lee. Pushed the wrong button. Sorry about that. I wonder if that's the problem everybody's worried about. There we go. Today, well, in 2013, that same average sedan vehicle cost around a little less than $35,000, but with inflation, that's actually half of what $3,000 was back then. So the auto industry has managed to cut the cost of automobiles in half in that time period of going from zero automation to almost 100% automation. And they're giving a warranty that's 3 times as long. So basically, we have a vehicle that costs half as much and is 3 times as good. And a lot of it is due to the automation of robotics. So the question is, how do we actually apply that to heavy fabrication? So flexible automation is one approach, but we've sort of tried to carry that a little further. In flexible automation, we have offline planning, direct CAD to part kind of programming tools. We want to move to fixtureless or non-fixtured parts. We want the system to be adaptable on the fly, and I put the little star there because I'm going to say some more about that a little bit later on. And we really want to look at computerized QC and QA. It's absolutely standard practice in the auto industry when you have a robotic system that's making the parts to do real-time digital data collection and complete quality control of that part while it's being made. And today, if you look at welding and shipbuilding, we inspect and we radiograph and we do all these really expensive, time-consuming after-the-fact activities. But in the auto industry, standard practice is do your QC and QA right there when the part's being made. Automatically put it into a database, and you have complete quality control records of everything. So that's another big advantage of this. So this top standard robot programming really works for the automobile industry, and I think this is what we need down here for the shipbuilding industry. So I got a couple of examples of how we've been pursuing this. This is a standard press brake used for bending steel. You apply 40 or 60 or 80 tons of force to it and do it long enough and have a 5-man crew and move it around a little piece at a time, and you can bend a plate. But that's a $7.2 million piece of hardware, and $3.4 million of that is installing it because it requires a 17-foot thick reinforced concrete foundation and a number of things like that, plus the huge number of people to actually operate it. And you got to have a crane standing by because the plate gets moved in that thing by a crane. This is an example of how we can do essentially flexible automation, and theoretically this will run a video. This is a thermoforming machine, and it's basically bending a 10-foot by 40-foot steel plate, and it's doing it entirely under sensor control. So it's got 32 degrees of freedom. It's got about 14 different sensor systems built into it, and it's actually bending the plate to shape based entirely on data that it got from the CAD drawing with no human intervention. So the end result is we have a machine that costs quite a bit less to install and operate, and it doesn't require a lot of human activity to make it work. All right, so here's another example. This is a manual process, basically straightening plate, and it takes 2 people because you got to have a fire watch on the back side of the plate. On average, we're looking at about 228 square feet a week straightened by this approach. and about $17,000 worth of energy costs per year. If we switch to a system, a portable robot system that uses induction heating to basically do the same job, this is actually a small robot system that we built that can come apart into 50-pound pieces, can be carried down inside the ship, put back together again, all in 9 minutes. Once the system is in place and operating, only one person is required to operate it. It can straighten about 1,510 square feet of deck plate a week. And its total annual energy cost is only $500. Because so much of the energy from that flame torch is just lost to the atmosphere. Plus, the process depends on heating very quickly and cooling very quickly, and a torch can't do that. So here's what the system looks like in operation. And now, basically, it's what I call semi-collaborative, in that the operator moves it into position and locates the 4 corners of the area that it's going to operate in, and then it measures the deck itself and makes its own decisions about what it's going to do, straightens it, measures it afterwards, can produce a quality control report. But the human being is actually not involved when the robot's running. They just set it up. So it's semi-collaborative, I would say. Let's see. That's a picture of it in operation. Okay, so in the welding arena, we have a need that we want to fill. The shipbuilding industry has a huge shortage of skilled, trained welders. Our workforce, according to the American Welding Society, is actually over 50 years old, average age. Training isn't going to solve the problem because it takes time. Our local community college, that just to get the basic AWS certificate takes a year. So how long is it going to take to train 8,000 people, especially to the skill level required for shipbuilding, for example, is not going to be easy or fast. It's going to take a long time. And those people don't develop those skills during that training process. They develop those skills in actual practice. Skilled workers are expensive. 50-year-old people who are skilled welders make a fair amount of money. They also have human limitations. The environment they have to work in, their age, their lifting capacity, all decreases. And interestingly enough, we also have pardon the term, a whole army of disabled veterans who, if we could connect them up to using a robot system, could be very productive and have a path forward in terms of employment. So we see the solution is to increase the productivity of the workforce we have, provide for extended careers for those people, take advantage of the existing skilled workforce, and reduce the cost actually by increasing the productivity of those people, provide a better working environment, reduce impediments to production, and provide a path to employment of disabled veterans. The solution we see is cobots, basically. So the goal of this project was to actually put together one and demonstrate to people that it would work, that it was possible to hook a robot system that was mobile up to a virtual reality control system and produce welds that meet the quality requirements and also increase the productivity level of a good skilled welder. So we started out by putting a computer model based system into it so that we can provide feedback, because now we have a human being that may be several hundred feet away from where the weld is being made, and so they need more feedback than they get just by looking at the weld. So we build in some kind of interesting things, and in the process of this, we collect now voltage and wire feed speed, which we could do for manual welding. But the thing we can't do for manual welding is we can't capture travel speed data, we can't capture torch angles, we can't capture the torch location. And so the end result is that we can't, with manual welding, actually do quality control of that weld. But with this COBOT system, we can do real-time digital quality control, which is based on the model. So we give them a virtual reality environment in which they're actually getting constant feedback about what's taking place with the weld they're producing. All right, so here's a video of John Gaffney, who's our welder guy. And he's in our booth downstairs, by the way, if anybody wants to see the system. And so when he's welding, the system is actually tracking the torch, generating instructions, duplicating both on the computer screen and with the robot torch itself, all the motions that he's going through and the activities that are taking place. And then as feedback afterwards, he has a whole series of, in the upper left-hand corner, of indications. So that one is, I can't see it with my glasses, so I'll lean over here just a little bit. So there was work angle, travel speed, torch offset. So all those things are built in, and he can look and see how well he was doing, and he can do it live, or he can do it after the fact, but we can get a quality control report for that weld. All right, so with that sort of background, let me talk about the system design. How am I doing on time, Lee? Okay. So we put together a precision welding system. It has a magnetic tractor. It's like a miniature bulldozer with treads, except they're magnetic, so it can crawl around on the ship. It can weld on a vertical surface, or it can weld upside down if we need it to. It has a unique suspension system that allows the robot to have a very stable base as it's moving along, because those treads do tend to do a little bit of movement. It has a smart torch management system, so we can do things like weaving, and if we have the right sensor, we can even do seam following, which is helpful because we're trying to push the speed up tremendously, take advantage of the skill of the welder, but allow them to weld faster in the process and increase the productivity, which helps the ROI for the system. It has a onboard wire spool and feeder, but we can also do it off-board. In the auto industry, most of the time, they have these 600-pound packs of wire, and they're fed through a system with a push-pull feeder system, and we can do the same thing. We can put a 600-pound pack of wire on the ground with a push feeder and then a small pull feeder on the robot. These are some of the capacities, and I like to point out, most importantly, I can carry 100 pounds, which means that I can put a big, heavy-duty, water-cooled torch on that robot that a human being is not going to be able to carry around all day, but has enough current capacity that I can dramatically increase the speed of the welding process. It also can travel at up to 150 inches a minute. So I have no limit in terms of how fast I can actually move the robot and therefore increase the travel speed of the weld. So that's what that tractor looks like. We add a high capacity power supply. The onboard feeder, as I mentioned here, is actually just a Miller feeder that we take the parts out of and put into the robot, and then a very heavy-duty welding torch. That gives us the possibility of doing a lot of interesting things in terms of moving very fast. So 675 amps, 1/8-inch wire, 900 amp water-cooled torch are what we have capable for the system. We have weld joint tracking built into it. It's a laser-based tracking system. And it gives us feedback, of course, for quality control, but we actually have a software system that's running on the robot that takes that tracking data and guides the main tractor, if you will, and actually gets it to follow the joint. So the welder now doesn't have to do a lot of movement with the torch to stay in the joint. The robot takes over part of that work for them. And so if we're getting them to weld at 3 or 4 times the speed they normally would run, we have that system built into it and available. We have a lot of communication capability built into it. So that's basically what the robot system looks like. The control system we use is a Parker Hannifin ACR 9000. Interestingly enough, their booth is right across from ours downstairs. So if you come down, you can see them. Those are some of the capabilities of that system. The other thing we're using extensively is a camera made by Visible Welding, and that camera is a high dynamic range camera and allows John to actually see not only the arc like he would see through a mask, but all the surroundings at the same time. And so he gets that data real time. So this is basically what it looks like when he's doing welding. There's the torch. There's what we call the nanny cam. That's a wide angle camera so he can guide the robot to where he's going to be when he gets started welding. That's a Visible Welding camera, and then the yellow spot down there is the Visible Welding screen that he's seeing. And when he's welding, you can see he's watching that Visible Welding camera. Interestingly enough, Steve Edelson, who runs a Visible Welding company, has a new feature that he's selling to training systems. He has a great picture of a weld instructor standing next to a student with his hand up here, not looking at the torch, but watching it in the camera view, because he can actually see more than if he puts on a mask. So we like that capability, actually. And there's all those same systems on there. So that's basically what the system looks like in our lab when it's running, and you can see it downstairs. We have the robot running downstairs as well, not doing live welding, but running. That's the sort of a close-up of the robot. You can see the wire spool and the robot arm enclosed there, and the torch down in the far bottom left corner of the picture. The virtual environment you've already sort of looked at there a little bit, and you're welcome to come down and take a look at it downstairs. So that's basically the overall virtual reality system. We are also starting to put augmented reality into that real-time video, so we can give feedback to the welder as they go. So we're capable of producing pretty good welds. There's a video of John actually making a weld with it, and that's an example of one of the welds that he's made that we measured to make sure it meets all of the code requirements. So, any questions? Yes?
So what's your estimate of the increased weld speed that you'll be able to achieve in a production environment?
Production environment, I don't know. This was a feasibility approach. John can pretty easily weld at 4 times the speed that he typically would weld. He's not the best welder in the world, so I don't know. You know, that's just one statistic to look at. But he's told us several times he thinks he can go faster. But we have a pretty short test, place in our lab, so we can't crank the speed up too fast. So I don't know how fast we can go. How fast can you go with any, fully automated system? 50, 60, 70 inches a minute maybe.
Do you
Yeah.
anticipate being able to have a single operator operate multiple systems at some point so that adding more self-control, more automation to the system?
Yes. The scenario we've kind of put together would be a skilled welder who's kind of an expensive person and a helper, and at least 2 robots. So the helper manages the cables and that sort of thing, and the skilled welder can just switch the virtual reality system from one robot to another. Whether we could run 3 robots that way, I don't know, but we feel like in terms of timing, it looks like 2 could work that way. But if you look at what a welder costs with overhead, you multiply that by 4, the ROI on this thing is less than a year. Yeah, that's all right.
Some questions about safety. Are there, obviously we've got the person away from where the weld is going. That's obviously a benefit in terms of safety. Induction heating, though, I've heard some concerns about issues of current and extra heat in the location. So any sort of general thoughts about safety issues, assuming the system moves forward to production?
Mm-hmm. Well, we're actually not using the induction hybrid process with this robot. It can carry the weight, So potentially we could do that. So there's from the induction standpoint, there's no issue here, at least not right now. Of course, you always worry about the robot, but there are ways of physically constraining the robot with cables and all kinds of other things to make sure it can't get very far away. And then you can build a lightweight cage around it so people can't get into that. I mean, we're going to be demonstrating the thing at FabTech, and we just have a little cage around where it's operating that's 24 inches away from the furthest reach the robot has, and that way we don't think anybody's body parts can get in there. But those are really good questions. Yes?
Do you have any yards actually testing this now?
No.
How far away is that?
To put it in production, we're probably 3 to 6 months away from doing that. The robot system isn't hardened at this point, so if you're going to put it in production in a shipyard, you got to worry about weather and all kinds of other stuff. In terms of being able to test it in a production-like environment, I think we're there. We could do that now, but I'm not going to put this robot outside right now until we figure out what we have to do to harden. The robot arm, for example, is really not designed to work outdoors. We have a sheath over it, but it's not waterproof. So there's a lot of things like that we're going to have to do before we can put it in a production environment. Yes?
So do you imagine this as kind of a shop type environment? This system, I'm trying to imagine it in a tight ship compartment where you make maybe a 4-foot weld and then have to move it to the next section or something. It seems like that would be a lot of setup time.
Right.
Drive down the ROI.
Right, and I don't think that's the best suited place for it. I think making long welds on a hull, for example, making long welds joining, deck together from two, ship modules. Those are the kind of things I think where it will shine. Could be useful in doing some things in a panel line, for example, because it's going to be a lot less expensive than a huge gantry, automated gantry system. So we have smaller shipyards that are looking at it from the standpoint of welding on stiffeners and that sort of thing. But this is the first prototype, I mean, you look at the first drones and compare them to what we have today, and there's just a night and day difference. So. Okay. Anything else? All right. Oh, yeah.
So the driver of the information about the weld to be done, are you anticipating that will come from a 3D CAD model?
Could. For example, on the deck plate straightener, the operator enters, where they are on the ship, and then it makes the determination of whether it's a weather deck or not, what the thickness of the material is, and then it knows what the specs are in terms of straightening. And I can see us to some extent doing this, but I think, you're going to have a welder. You're going to have a skilled welder doing this, so they're smart enough to not make those kind of mistakes already. But giving them lookup tables or references or information out of the CAD drawing, as CAD systems start to actually have, start to use STEP and have full, manufacturing data built into them, then sure, we can provide huge amounts of information to the welder. The other thing we can do is check and make sure they're welding with the right electrode and they're using the right gas and all those sorts of things. They won't like it though, because we'll be able to tell everybody how many feet of weld they make every day.
On the back end, do you see having the result, the quality information fed into some database for maintaining that in the long term?
Absolutely. Yep. The system's already designed to do that. It can talk via Wi-Fi. It can be plugged into a wired system. And I didn't show it, and we'll show you if you want to come down to the booth, but we have a whole quality control system, captures all that data into a database, and so yeah, we can automatically put that into a QC system. Right.
We'd have to cut off the presentation. Jeremy's going to be here this afternoon. Follow-up questions? Sure.
Booth 429. Thanks, Lee.